We use the first law of thermodynamics, the law of conservation of energy. We have been using it for all these videos and all these slides to calculate energy changes involving chemical reactions, so changes in enthalpy. But what we haven't worked out is actually if a reaction is going to happen or not. We know that if it happens, it will release heat and it will be exothermic, or it will absorb heat and it will be endothermic. But at the moment, I haven't given you any tool to predict if a reaction is going to be spontaneous or not, or that's going to happen. Okay, exothermic reactions are spontaneous because they have enough energy. The reagents have enough energy to make the products and have some energy to spare in the form of heat. But what about endothermic reactions? Does that mean that they never happen? They are never spontaneous? Well, the answer is no. Some reactions are endothermic, but they happen spontaneously, which might sound slightly counterintuitive, and we'll look at it in the next few slides. But no, there are endothermic reactions that do happen spontaneously. And the two I've got here, the dissolution of potassium chloride, solid aqueous, so dissolving potassium chloride in water, or the decomposition of dinitrogen oxide, N2O4, with a little bit of heat to produce NO2, they are spontaneous reactions. So just knowing if a reaction is going to give heat or absorb heat, if it's going to be exothermic or endothermic, is not enough. We need to introduce a new variable, a new concept, and we call that concept entropy. There are a multitude of definitions of entropy, from the simplest ones to the most complicated ones. For the purpose of what we're discussing here, a reasonably simple explanation does the job. Entropy is the way we have to measure the disorder of our system, the disorder of our chemical reaction, the disorder of our physical system. So an entropy measures how the tendency of that system, of that chemical reaction, towards dispersal, towards a disorder. So the more disorder, the greater the dispersal, the more disorder from before to after the reaction happens, the greater the entropy change. And when you have a spontaneous change, the total entropy of the system and its surroundings must increase. So the change in entropy from before and after the reaction happens is a positive number. When you have an exothermic reaction, they have delta H going for them. They have a change in enthalpy being favorable. Why? Because the reaction releases heat, it warms up the system and its surroundings, it gives energy to the molecules that they move, it increases the dispersal, it increases the disorder, both of the system and of the surroundings, because you're increasing the temperature of the surrounding areas. So what about endothermic reactions? Can they, at least sometimes, increase the entropy, the total entropy? And the answer is yes. Endothermic reactions, yes, okay, there is no energy, heat being released, so delta H is not favorable, but some of them involve reactions in which from the reagents to the products you have lost order, so they are more disordered system. There is a dispersal, an increase on entropy, and if the increase of entropy is good enough, large enough, the reaction will happen. In the dissolution of potassium chloride, you go from potassium chloride and you dissolve it in water, and you end up with potassium chloride aqueous. And if you think of what that means, it means that you have potassium ion and chloride anions. That's what it means. You have an ionic compound, the water molecules split that ionic bond, and suddenly you have the ions of potassium and the chloride anions surrounded by molecules of water. You have a more dispersed, a more disorganized, a more disordered system. So the entropy of the system has increased. In the case of the dinitrogen tetroxide, N2O4, they're both in gas form. You heat it up slightly and you produce nitrogen dioxide, but you produce 2 moles of nitrogen dioxide. So you have more moles of gas in the product side than in the reagent side. So again, you have you have increased the dispersal of the system, the disorder of the system. The change in entropy is large enough for the reaction to happen. because you have more moles of gas in the product side. So when you're trying to predict will this reaction be spontaneous or not, you need to look at both things, the enthalpy of the reaction and the entropy of the reaction. And if you have an exothermic reaction, then that's fantastic, because that you increase they naturally increase the disorder of the system because of the heat they release. But when you have an endothermic reaction, you have to start thinking, okay, it does need some heat, but on the other hand, does it increase the disorder of the universe, the dispersal enough? Is a change in entropy enough that it can compensate with the fact that it needs some heat for the reaction to happen? And that is not a decision that can be taken easily. You will need to be all the time thinking, or having specific values for enthalpy, specific values for changing entropy. So we need a third thermodynamic variable, something that allows us with one number and whatever sign it is to say, yes, this is going to be spontaneous, no, this is not going to be spontaneous. The same as we use delta H, and we say, oh, this reaction is exothermic, reaction is endothermic, and we need nothing else. We need to know nothing else but the sign of that changing enthalpy. So we need another thermodynamic variable that link the changing enthalpy with the change in entropy. And we do have one. It's called Gibbs free energy. And again, we cannot measure absolute values, but we can measure the change. So we can measure delta G, the changes in free energy. And it links both the enthalpy, changing enthalpy, and the changing entropy. And they are linked by the temperature. So, depending on the temperature and the change of entropy, it is possible for a reaction to be spontaneous or not. But you don't, depending on what the changing enthalpy is. But you don't have to look at the details, what's the enthalpy, what's the temperature, what's the entropy. You just need to know this value, calculate it, measure this value. So delta G, the change in Gibbs free energy, will tell you if a reaction will occur or not, spontaneously. If delta G is a negative number, then the reaction is spontaneous. If you have a delta G value, a change in Gibbs free energy, which is a positive number, then the reaction will not be spontaneous. So, delta G negative, the reaction is spontaneous. Delta G positive, the reaction is not spontaneous. And interestingly, we have a third case. What happens if delta G is 0? So it's not negative or it's not positive. Is it spontaneous or not spontaneous? Well, the answer is both spontaneous and not spontaneous at the same time. The reaction is what we call in equilibrium. And more about that in future videos. So for now, just keep that in mind. You've got delta H that tells you if a reaction is going to be exothermic or endothermic. You've got delta S and change in entropy that tells you how disordered the universe will be after the reaction has taken place. And you have delta G, the change in Gibbs free energy, that links both concepts and the temperature, and it's a quantity, it's a value that just by looking at the number and looking at the sign, positive, negative, or negative, you will be able to predict if a reaction is spontaneous or not.